All right, so in today's environment class, we're talking about cooling a greenhouse. So the different strategies and some of the things to consider. Um, Obviously, one of the first things we do for cooling a greenhouse is shade. We've mentioned shade a few times this term in terms of energy curtain and blocking light, which also reflects heat. We'll spend some time talking about ventilation today. So there's different kinds. There's forced ventilation. This is where fans are involved. There's natural ventilation. This is where warm air is lighter and rises so that when you open a vent at the top of the greenhouse, the hot air escapes. Then we'll talk about sort of open roof, open side concepts. And then we'll touch on evaporative cooling uh, and try to explain a couple of things which hopefully you grasp, and if you don't worry, we're going to be covering it again in the winter term with your computer controls class. Um, Heat pumps is something it's on the list here, but I deleted it because it's really not common. It's maybe some research universities are using it. That's essentially where you're using electrical pumps to pump heat out of the ground, like a kind of like a reverse fridge, and heat the greenhouse. But that's really not used. There's only one greenhouse I know of in the world in Germany, and it's highly subsidized by the government. So let's not waste too much time on that. We got enough material to cover. Um, this slide, to some extent, is a review, but it's just another perspective showing the red lines where heat is involved and blue lines where heat is lost or cooling happens. And the yellow is just ventilation, right? So we have obviously the sun is our biggest contributor to heat, unless you live over a volcano. So it's basically the number one source. Um, that heat is stored in the greenhouse. In the greenhouse this week, we talked about how the concrete floors act as a heat sink, but not to mention all the soil that's underneath the greenhouse acts as a heat sink, and that stores heat, and that also re-radiates it later. So the other options are convection, so that's where air touches a warm surface, warms, and then rises away, taking heat with it, and that cools the surface as well. We see that in terms of just air moving over plants and over structures like the concrete. And then there is external heat loss as well, and that is where cool air touches a warm greenhouse and removes heat. The most obvious of that would be in the winter when a cold wind blows across a greenhouse. It's actually convecting heat off the surface and removing it with the cold air as it touches it. Another thing to keep in mind is that irrigation. So when you sprinkle a crop, whether it's overhead or whatever, that water, that cool water cools the air, not only through evaporation, but just from the fact that oftentimes the water is a cooler temperature. So a lot of things going on in a greenhouse in terms of heat being stored, radiated, and absorbed. So let's review shade a little bit, right? So it reduces incoming radiation. We talked about how in tropical climates where it's really hot, the shade is on the exterior. We talked about whitewash, and then it can also be inside the greenhouse. But one of the downsides is that shade also reduces light, right? So yeah, you block the light because you get less heat, but you have less available for photosynthesis. And then lastly, you get less air exchange. So if this is your greenhouse, there's say a couple of peaks or gables, right? There's our greenhouse. And I have an energy curtain, right? And say it's hot and I close it all the way. There's lots of heat that's going to build up in this area here. And the greenhouse itself will stay cooler because it's shaded, right? But this heat here will also continue to radiate down. So it's not a perfect situation. That's why in tropical climates, the shade is often exterior to the greenhouse because then the heat isn't trapped in the gables. You don't have this situation. And it also permits heat then to escape the greenhouse if you have vents open underneath so that heat can escape the vents. So in really hot climates, this is fantastic. Now in our climate, in temperate climates where there's winter, snow and stuff like that, we can't do this because the snow load would land on this and it would tear it apart. And it's too much work to install one and remove it every season. So Whoops, I just deleted our gables. So generally speaking, in temperate climates, the shade is inside the greenhouse. Wow, let's just get rid of this stuff. Which of course means that there's less opportunity for air to move into the greenhouse proper because it's covered, right? You can't get fresh air getting through. So we reduce our air exchanges. That has implications for humidity management and things like that. Um, Generally, it is difficult to modulate the temperature, right? So what we can do. Let me draw another little greenhouse here. Bear with me because I'm doing a lot of really crappy drawings in this slide. What we can do is we can have the curtains open a percentage. So the computer would say, okay, go 50% closed, right? And then that blocks, let's say you got a 50% shadow on your crop. So that's 50% less sunlight that's hitting your crop. So in theory, you have 50% less heat. It doesn't always work out like that. But the bonus is that if your vents are open, air can escape through the gap that's not closed, right? That's beneficial. One of the downsides is that more often than not, where the sun is not blocked, you get intense rays of sun coming through, and you can often burn stripes across your crop. So I mentioned this in class once before, that in modern greenhouses, they're very tall and they often have 2 layers of energy curtains. So what they do there is the bottom one overlaps the top one. So there's no light gets through, but air can escape between the two. Now in the college greenhouse, it's too short for us to accommodate 2 layers of shade. But in a lot of modern greenhouses, ones built in the last 5 years, this is what we're seeing done. Forced ventilation. This is with fans, exhaust fans. This is a typical fan. These are called ERM fans. They are set up in such a way that when the fan starts to turn, they spin some weights, and those weights act on a plunger, which then pushes the louvers open. So there's actually not a lot of moving electrical parts. There's just one motor to make the fan turn. They're very common in greenhouses now. And they're often accompanied by a vent along the wall on the opposite side of the greenhouse to let cool air into the greenhouse as it's sucked in from the fans on the other side. So typically the fan pushes warm air out, not in, not cool air in, but warm air out. The intake vent is always opposite the gable walls where the fans are. And it typically is a pulsing system. So the fans are on or they're off. I've seen farms try to experiment with variable speed fans. It doesn't really work because the way the fans are designed, they're designed to operate in a very narrow RPM range. So if you lower the speed, what ends up happening is more air is just spun in a circle than actually moves out of the greenhouse. So just be mindful of the fact that that's not necessarily beneficial. It gives you some percentage of control, but not a lot. So typically these are just pulse. The computer will just pulse the fan on for whatever, so many minutes or seconds, and then shut off, and then monitor the temperature change and keep pulsing it. In the winter, this is excellent because it allows us to sort of just turn on 1 or 2 fans to bring in fresh air. Remember, we're always concerned in the winter that we're going to end up with too little vapor pressure deficit, which means very high humidity. So by venting air out of the greenhouse and bringing drier, fresh air in, we can maintain a suitable humidity for the crop so that they can actually transpire. So fans are often seen, especially in ornamental greenhouses, in combination with natural venting to make sure that in the winter months they don't end up with a poor environment. In the summer, it can be stressful on the crops because your fans are running so much that it's so dry that you actually cause stress. Remember, if it's really dry, below 20% humidity, 25% humidity, the stomata actually close. And then the leaf temperature skyrockets because there's no evaporative cooling and your plant's not breathing in fresh CO2. So the growth stops. So there are challenges when it gets really hot where fans really alone are just not suitable. Um, an important consideration with fans is their location. And what I'm trying to show with these arrows is the height of the greenhouse and the height of the fan. Uh, if you look at this cross section, the fan is located almost at the halfway mark of the height of the greenhouse. So when it's exhausting hot air, it's pulling hot air off this level. It's not touching the upper layer. So in a sense, that's really a poor design for cooling the greenhouse per se. Um, there's two schools of thoughts on this. You know, if you leave this part alone, you're at least managing the thermocline where the plants are, but more often than not, a higher fan or a combination of the two, where one is located up near the above the energy curtain in combination with below, is a better idea. So we want to think about it from a vertical perspective, because remember, hot air rises and cold air drops. So in this situation here, we have gable fans that are above the energy curtain. This, and if you look down here, this picture doesn't show very well. I don't know why I cropped that out, but there's fans down at the bottom. So here we have a combination of peak and lower fans at the level of the plant canopy. This is an ideal situation for keeping the best climate, because remember, these curtains are closing. The air above the curtains ends up static. It gets very, very hot, and that radiates through the cloth, contributing to radiant heat, which you cannot blow away with a fan. So we need to get that air out of there above the energy curtain. Here's another good example. This is the one I was thinking of. So you've got your fans down at the level of the plant canopy, and then you have an upper gable fan. So you can see where the blue line is where the threshold of your comfortable climate is going to be. So this is really what you should be doing. If you're driving along the QEW and you see the old Up Cannabis facility, you'll notice that there's fans all along the wall, all the way down the greenhouse. This is near Grimsby. And it's a horrible design because they have no fans in the gable. And I know for a fact that they struggle with incredible heat in the summer. And it's a design flaw. And they just built a whole second half. It's a new company now, but they built a whole second half the exact same way because they just didn't listen to what was being told. Anyways, so this is just showing you sort of the idea that cold air comes in and we're exhausting out the top. Just try to remember, think of the air in terms of warm air rising, cool air dropping, and when you're removing it with fans, think of what levels are being removed. That's what I'm after here. The other thing to consider is the length of the greenhouse. This is one of the limitations with gable fans on a long hoop house. Like, look how long this thing is, right? And it's one thing for cool air to come in this side, right? And hot air to exit. But what happens along the way is that the crop closer to the end where fresh air comes in is comfortable, and the end towards the end where the fan is overheating. So as far as crop growth is concerned, what you actually see is you see normal growth and then stress growth as you get closer to the end where the fan is, because it's just not enough cool air making it to the other side. It's just too far. Really long hoop houses are best combined with a roll-up side. So the idea is that a side rolls up here, the plastic rolls up, exposing the entire side to fresh air, and usually it should be both sides. You can't combine roll-up sides with a fan though. If I had a roll-up side all the way along here and all the way along here, and then I had a fan in the gable at the end, instead of drawing air the length of the greenhouse, what's going to happen is it's going to short circuit and it's going to draw air from the side right up to the fan and go out, and none of this air will be exchanged. So a fan with roll-up sides is not a good combination. So summarize, exhaust fans are in the gable wall, push hot air out. Intake fans are always opposite to allow cool air in. It is an on-off scenario where you pulse the temperature down with the computer. In the winter, they are very advantageous for maintaining sufficient vapor pressure deficit to keep the plants active. In the summer, too much ventilation is stressful. And then lastly, we have reduced efficiency over long distances, right? So you end up with cool on one end of the greenhouse and hot at the other and an uneven crop. Let's look at fan and pad cooling. It's a lot like someone putting a damp cloth on their forehead when they have a fever. As the water evaporates from the cloth, it creates a cool cloth, which helps take heat from your forehead, right? Um, Evaporative cooling has been used for since the late 60s, actually. It is used in like orchid greenhouses, greenhouses where crops are grown that are, not really tolerant of major temperature swings. Um, some pepper houses had them in the early days, but now we have varieties that handle the temperature better. But essentially, what happens is you have a wet pad. This is a close up. It's just basically like cardboard, kind of a convoluted structure. And water trickles through all the fibers, so it's soaking wet. And then air blows through the holes, picks up the moisture, and in the process cools. Just like, whoops, just like the just like the cloth, the wet cloth in the forehead scenario. So water evaporates in the airstream, and that liquid to vapor transition. So when water goes from liquid to vapor, there's an interesting thing called enthalpy, which happens where in order for water to turn from a liquid to a vapor, it has to absorb energy from the surface that the liquid was on. So when water evaporates off this cardboard, it physically cools the cardboard, and subsequent air that comes through is cooled by that cooler cardboard. This is a concept that you need to understand because it's related to leaf temperatures being cooled by evaporation as well. So remember, like stomatoconductance, the fact that water is exiting and evaporating from the leaf leaves a cooler leaf behind because of the evaporation process. Um, this is just a picture showing like a water reservoir that trickles down, keeping the cardboard wet. And then your outside warm, dry air comes in, picks up the moisture, and as the water is absorbed by the air, cools the surface, which in turn cools the air coming in behind it. Now, to look at this on a chart, and again, we're going to cover this in the winter term with your greenhouse computer class, but uh, bear with me as we look at what's called a psychrometric chart. And this is how we determine how much cooling will happen in the air based on different humidities. So if we start with 40 degrees Celsius, all right, and we go up to 10%, so the number one here, we're looking at number one, 40 degrees Celsius at 10% relative humidity. So I go from here, I go up to 10%. So this blue line here, that's the 10% line on the chart. This is the 20% line, the 30% line, the 40% line, the 50 or 60, et cetera, et cetera. So we take our temperature of incoming air of 40 degrees and 10% humidity. All right. Then we're going to slide on these diagonal lines. These diagonal lines are our enthalpy lines. We're going to follow that angle until we hit the next humidity, so 45%. Say we go from 10%, so we're adding water to the air. So we go from 10% all the way up to 45% relative humidity. And then we go from this intersect down to the temperature, and you can see that it's 27 degrees. So we went from 40 degrees down to 27 degrees just by adding moisture to the air from 10% to 45%. We're just past the 40 here, 45. Right? That's what they consider comfort zone. That's fairly dry, but another scenario, if you look at going from 40 to 100% humidity, so 10% to 100%. So we're going to go from a low humidity all the way to saturated, would cool the room down to 18.5 degrees Celsius. In southern states, Georgia, Arizona, some parts of Florida, Texas, these coolers, this air conditioning that's done using this, they're called swamp coolers, where they effectively have a fan surrounded by paper pads, and it cools the air. Or if you happen to have a humidity a humidifier in your house, one of those portable ones, they have a paper or cellulose pad that dips into water and it blows air through. If you put your hand over it, you're going to notice that the air is quite a bit cooler coming out of that than there is the air temperature in the room. It's exactly the same thing that's happening. So as we add moisture going from low humidity to high humidity on these enthalpy lines, we effectively lower the temperature. So there's another picture of a fan and pad. Mostly I see these at research institutions. They're expensive. They require some work to maintain. You got to keep the cardboard clean. Every 10 years or so you have to replace it. It's not that expensive, but it gets algae in it and calcium plugs up the cellulose fibers and less water is absorbed. It just starts losing its efficiency. Again, related to when I talked about having a fan in a long greenhouse, if we had fresh air coming in here and exhausting out here, we have an issue with the fact that it's such a long run that the temperature starts to increase as you move towards the far end. So typically with fan and pad, the fans are opposite the pad, but they're on the long side of the greenhouse so that we have a shorter distance to travel. So a shorter distance means there's less of a variation in temperature across the greenhouse as opposed to going the long distance. All right. Natural ventilation. So this is with vents. So that's how we cool the greenhouse at the college. In the sense, the idea is for some level of control, you can vary how much the windows open. So they're at the ridge of the greenhouse. If they open a little bit, small amounts of air leak out. If they're open all the way, lots of air leaks out. There's lots of different styles of top vents. There's also side venting, which is often in combination to let cool air in lower. So I want to look at a few examples here. This is a common Venlo style. You'll notice that the vent, which is only partially open, is not the entire length of the gable. It's about 50%, so it's about halfway. That's really important when it comes to talking about things like snow load in the gutters, because you can have snow piled high in the gutter and the vent can still open without any risk, or less risk, let's say. Then there is full vent. This is the whole roof opens. There's some greenhouses like this. Oftentimes, growers that grow semi-perennial or perennials have a greenhouse like this because towards the end of the season, they actually open the greenhouse completely and they let natural unfiltered light and rain hit the crops to harden it off so that those perennials are ready for planting in someone's garden. There's less of a shock. Then there's double poly greenhouses. These are double inflated poly where the entire gable roof moves to open and close. So these are called gutter vented poly houses. So these are all different styles of vents that exist. What I want to talk about in the next few slides is sort of try to envision how air flows through the greenhouse and what that means for temperature regulation. So in this example, we have side vents and we have gable vent, ridge vent. So these vents are at the ridge of the greenhouse. And if you track the flow of air, air can enter the side and exit the other side. It can also enter the vent and exit the vent. And to some extent, you get a general cross flow over the greenhouse. And that's not too bad. That's a decent scenario for cooling. If you don't have any roof vents, there's no way for the heat to escape, and you end up with hot air kind of circulating above the canopy, just like when you have exhaust fans without a gable fan, right? Or at the peak. So fully open roof vents, excellent options for control. I've seen these in operation. They do have limitations, which is why you won't see them with a lot of ornamental growers, mostly perennial growers. And that is that when the vents are closed, remember how I said vents can be, anywhere from 0, 10, 20, 50% open or 100% open. Typically with these ridge style full roof vents, it's very difficult to have a very small percentage open because you have this huge crack all the way down the length of the greenhouse, and it lets a lot of hot air out. So it's really difficult to modulate. Um, so a lot of growers have not opted. Plus, you're lifting all the glass in your greenhouse up. So the amount of electricity to actuate these vents is substantially higher than normal vents. Um, Plus, there's a lot of maintenance. And then think about this. Let's say it snows in the winter, right? So there's our roof. We got a little bit of snow piled in here, and now you want to vent. These are going to come together. Look what happens. The snow is going to get stuck here. It's going to smash all the glass at the bottom of these vents. So there's some very serious limitations to this. And by the way, you don't have to open them that extremely. If there's ice, ice doesn't move. You can't compress it. The second you move these even an inch, it smashes all the glass. And we're not talking a few vents, we're talking the entire roof. So that would be a colossal error from an operator or a grower's perspective. Um, Roof vents in a peak greenhouse, this is when there's no side venting whatsoever, right? So in this case, the vents open and hot air escapes. Maybe there's a wind direction which biases it so that more hot air is escaping on the downwind side, and a little bit of cold air comes in, falls down because it's heavier and settles into the greenhouse, right? There are some different scenarios where this may or may not work. Now, a lot of farms are like this. This is how they work. And for the most part, your plants are sitting in this area down here. Even in a high wire tomato greenhouse, they're so tall. They're maybe 30 feet to the gutter, and they're using up 15 feet for plant growth. So you've got all this air up here. So it's okay if there's some stratification. You have the cool climate where the crop is, right? Um, if you have side vents, this is more efficient in terms of letting heat out. It's sort of like breaking a vacuum on the structure. It's just lets air out really fast. But depending on the height of the side vents, you can actually create a dead zone. So if the vents are, say, 6 feet off the floor, you have 6 feet that is not going to get much air exchange and is going to be potentially very warm. Because warm and cold air don't like to mix, you'd actually get what we call a thermal inversion, and you have warm air stuck in the area where your crop is. So where these vents are positioned is often low in the greenhouse to prevent that from happening. This slide, I'm trying to help you understand a couple of terms here. There's windward and leeward vents. So windward is facing the wind, and leeward is facing away from the wind. So obviously wind changes. So from the computer system's perspective, it has a weather vane that tells the computer which way the wind's coming from, and it will revise which is the windward and which is the leeward based on the direction of the wind. Now, why this is important is because typically the vents that are facing the wind, which is the windward, so these ones, open less. So you have a smaller gap on this side, and the ones that are facing away from the wind have a larger gap. And that sort of allows you to scoop a little bit of air, allow this exchange, and create a negative suction to pull it out the top. There's a couple of reasons for that. One of them is also that if you have a strong wind coming and you have your vent, so here's my greenhouse, right? And I've got my vent sticking like this and like this and like this and like this. The wind will actually hit the vent and knock the glass off and send it flying and smashing. So we try to limit the vents that face the wind so that they don't open as much as the vents that face away from the wind. This is some models showing air exchanges in greenhouses. It's hard to see in this picture, but it is kind of interesting. And what they're showing is that when you have a very long greenhouse, the first gable gets the most mixing, and as you move further along the greenhouse, there's slightly less mixing. This is where having horizontal air fans, so HAF fans, to help distribute the air in the greenhouse helps even out that temperature. So they're often used, although when you have vents above a certain percentage open, the fans shut off because there's so much air movement from in and out that they're no longer useful and it's just a waste of electricity. Got some other scenarios here. These are from that paper. It was on the couple of slides back. Pretty interesting to see. This is sort of just thermal modeling using engineering software, looking at what happens in the greenhouse under different windy conditions. Notice in this model, they don't have the windward vent limited and the leeward vent more largely open. So that kind of impacts their model. I'm not sure what they were thinking, but uh, what this is showing though here is that the bottom one has high wire vegetables in the model. So they do impact the flow of air, right? In this one, we have a rapid stream of air moving across the bottom and out the other side. And here we have some slowed motion. So this first row is taking a bit more of a hit, but more of the greenhouse is actually cooler comparatively. So here we have sort of a longer infiltration of warm air. Here the air hits the first row and that's it. Then the rest of it is mixed well. So not to mention, this model doesn't factor in that plants, the more plant mass you have, the more they cool the greenhouse through evaporation. So again, a lot of high wire veggie farms are not nearly as hot as you might think in the summer months, except for cucumbers. Um, this is a chart from that paper that compares the different combinations of venting. And I've been talking about windward, leeward venting, right? So in this case, the best scenario is side vents and leeward vents. So they're open away from the wind. And we have very good greenhouse temperature. These guys are advocating this combination here. It may be slightly better, but remember what I said. This is sort of these things where academics that haven't run farms maybe miss out on some of the truth. The problem with this is that when wind hits this glass, it can lift the glass off and break it. So as a rule, most computer systems will limit the windward direction vent so to a smaller fraction of the leeward vent. So this slide is just summarizing that. So high winds can directly damage vent windows. Leeward, windward, side venting. Just this is a good summary of what I was talking about, so you don't have to write it down. Yeah, and if you have a real storm coming in, oftentimes this is situations where you kind of have to think, right? Like computers are great for running a greenhouse, but they don't always know everything. And we have situations even here in Niagara where a storm can whip in within minutes. And depending on your computer systems, they often have a delay, so many minutes before the vents move to prevent constant movement so they don't wear out. And if say your delay is 5 minutes, 5 minutes is more than enough time for a storm to whip up and winds to go from almost nothing to extreme. And that's when you get real wind damage. So it's important as a grower to not just rely on the computer, but use your head. If you know there's a storm in the forecast, you should already be careful and be monitoring the greenhouse. And if you see dark skies approaching, you're going to manually lock down your vents or limit them to a small percentage so that the glass doesn't lift off and smash. Typically, it is important to open the leeward side to reduce pressure. You can have situations where if all the vents are closed and a real storm blows in, the outside pressure from the greenhouse can drop dramatically, and that will cause the pressure difference in the greenhouse to sort of the difference can be enough that you can actually crack some windows. So just be aware of that. Lots to think about when you're operating a greenhouse. This is an example of wind damage at a greenhouse in Niagara. I think this is a Jeffries plant. Not only do you have winter damage, but you have summer storm damage. And Holland, which is has really high winds coming off the sea, has designed a lot of their greenhouses to withstand up to 120-kilometer winds or more. And that's great, but it still requires the operator to be on top of things to make sure vents are being operated properly and not catching the wind. Yeah, I already mentioned snow, so this is sort of summarizing that. The idea that, snow can get into windows, ice can form in gutters, and when you try to open the window, that restricts the movement and breaks them. Another thing I didn't mention was rain limiting. So a lot of systems will turn the vent or close the vents when the rain starts. So they have sensors that detect rain. I think Matt's going to get into this, so I don't want to spend too much time on it. That really is just to make sure that rain doesn't get on your crop, which is maybe a little over the top because, I mean, we irrigate our crops, right? But some crops, you know, if rain gets on the flowers, you can get botrytis and stuff like that. So I get it. One thing I wanted to mention was with these double poly greenhouses, there's two choices. You have what's called ridge vent or gutter vent. So on the left, you'll notice that the entire roof, this is double poly, right? So we can't break it into a small vent. It's very difficult. You'd have too much structure and changing the plastic would be a pain. So the entire roof opens. And here it opens at the peak, which is great because it lets the hottest air out. And what else does it prevent? It minimizes the risks of snow in the winter. So these kinds of vents can actually be opened in the winter, even when there's some snow, because poly won't break. It just gets deformed. Not a lot. They can't open lots, but enough more to deal with temperatures in March, where you can go from snow one day to +5 the next day and have really high temperatures in the greenhouse. Whereas this older style, the roof opens in the gutter. So you have it swinging from the gutter up. Clearly, that's not going to work if there's snow in the ridge. It's going to be too hard for the mechanism to operate, and it's going to bend these geared drives and damage the sprockets that wind them open. So this style greenhouse in Niagara is called Apex. It's made by Westbrook. There's copies. Other companies make the same ones. This is the preferable design over this older style on this side for those reasons. So side venting, I alluded to that, right? That where you open the sides, it's often combined with top venting. One of the nice things with side venting is you not only can you combine it with natural top venting, but you can also combine it with forced ventilation. And typically in the winter months when you have less heat issues, you can more gently cool the greenhouse with maybe just a couple of exhaust fans and then some air inlets to let fresh air in. Now, in the summer, one of the differences between forced and natural ventilation is that natural ventilation is not a windstorm necessarily in the crop. And so with less air movement, your canopy is less disturbed, which can be good, can be bad. For the most part, plants prefer gentle air movement. Extreme air movement, like I mentioned the other day, is good for affecting how plants grow structurally, but not necessarily the best for them to grow effectively or smoothly. So, fogging. This is where we often see fogging in propagation areas where we're trying hard to minimize stress. Remember, a cutting has no access to nutrients in the soil because it doesn't have roots yet. So we can apply some nutrients with irrigation water, but if you overwater, then they rot. So that gives you only so many opportunities to apply nutrients to the leaf. And once the leaf dries, it can't absorb nutrients anymore. So we try to keep the cuttings cool, especially in the summer months with fogging. High pressure fog works just like the Aquamat, or I mean, just like the vapor, just like the fan and pad, sorry, where you have sort of enthalpy, where as water evaporates from the surface, it cools the pad. In the same way, high pressure fog, you inject high pressure fog into the growing area, and as it evaporates, it absorbs heat from the air, cooling the air. And if we cool the cuttings, we reduce respiration, which means that the cuttings don't use up their own energy reserves as quickly. So they have enough stored in the leaf to drive the root growth necessary to get that cutting rooted. So fogging is pretty essential if you're rooting anything in the summer months to make sure that you actually have success. So it's an alternative to fan and pad. I can think of a few greenhouses in Niagara that use high pressure fogging. It's not an irrigation pump. You need a special pump. We're talking high pressure and very fine nozzles to get really small droplets. If the droplets are too big, they don't have time to evaporate before they fall out of the air and they end up overwatering the crop that's below it. So it has to be very fine mist. Yes, it can be used in combination with natural and forced ventilation. Obviously, you kind of have to make sure you're not wasting your energy on overdoing it. The mist has to evaporate quickly, which means you need a dry climate. Uh, but definitely in hot climates, this is something that we like to do. For example, one greenhouse that grows campanula in Niagara, which is a cool perennial crop. They grow it year round and they use a lot of fogging through the summer months to encourage rooting so that the plant thinks it's like cool like spring. Maintenance, yeah, with such fine nozzles, if you've seen drippers plug, you can only imagine how much these other ones plug. So you have to deal with the water treatment to make sure there's no calcium in there and stuff like that. There's a close up of there's a high pressure stainless steel line in the greenhouse, and then there's your fogging nozzle. Notice all the heating pipes. There's a lot going on here. High pressure fog lines, heating pipes. Looks like there's an electrical conduit. That's greenhouses for you. Lots going on. Um, so when we're talking about evaporative cooling by plants, we're talking about reducing temperature through evaporation of water from within the plants. So I've talked a lot about how having small, like say you have a 4 or 5 inch pot ornamental crop sitting on a bench, relative to the whole greenhouse space, that plant area is very small. So the plants will have somewhat of an effect on the climate, but not as much as a high wire crop that occupies a large percentage of the air volume. So partially filled greenhouse lacks much of the cooling effect from plants. And in the summer, it's tough to keep them cool just based on plants alone. Um, One of the interesting things here with improving a climate can be just putting water in a concrete floor. We used to do that in our greenhouse in the summer, and concrete walkways, we would just hose them down, and as the water evaporated, it helped keep the greenhouse a little cooler. And sometimes if you have sections where there's no plants, you can turn misting or sprinklers on and just wet the bench and the mat underneath, and that helps to cool the greenhouse because you can't overwater your crop, but by misting non benches that are not covered with crops, you can also keep your climate a little cooler. Just some tricks. One of the most important things from this lesson to remember is that a lot of all the cooling methods that rely on evaporation only work when the incoming air is dry enough. And so with that being said, evaporative cooling is very limited in Ontario because a good part of our summer has very high humidity. So if you've got 75% relative humidity in your air or 80% coming in, there's not much room to absorb much water. So your albedo, I mean your cooling effect is minimized because of that very small increase in humidity. So most often we see evaporative cooling working in very dry, hot climates like near deserts. So Texas, Arizona, those are very effective areas for evaporative cooling. Florida, I did mention, but truthfully, Florida's also fairly humid for good chunks of their summer. So swamp coolers down there are still used because they're inexpensive, but they are limited when it's humid out. So just keep that in mind. Um, that's pretty much it. So hopefully you track that. We will be covering this again with a little more emphasis on the computer control strategy in the winter term class. Okay, take care.